Hello everyone, this is video lesson 15.4. We're studying r squared and s in this video lesson. So r is the correlation coefficient, so r squared is that correlation coefficient squared. It's kind of complicated to calculate correlation coefficient, and it's even more complicated to then find the square of the correlation coefficient. We're always going to find it using our graphing calculator. So with these scatter plots, we use these scatter plots and the linear regression line to predict what's going to happen. And so if we use this least square regression line, we could predict what's going to happen somewhere within the limits of the data, but we are going to have errors. And the percent off we are overall can be because of our explanatory variable, or it could be because of other factors that are not our explanatory variable. So r squared tells us the percent of variation in our response variable that is accounted by the least square regression line. This LSRL stands for the least square regression line, or the line of best fit. So another way of saying the explanatory variable. If we take 100% minus r squared, that will give us the percent off we are because of other factors. Let's just say that it is the hours that we spend studying and the GPA that we have. We would generally say that the more hours we spend studying, the higher our GPA would be. But there are other factors that would determine our GPA. Maybe our IQ would be another factor besides the hours we spend studying. Maybe if we're studying with a tutor, or if we're studying by ourselves or with a group of friends, all those things kind of affect the GPA besides just the number of hours that we spend studying. So because there are other factors, we could be off slightly, so that's what r squared and s kind of cover. When asked to interpret r squared and s, we use these sentences, and I do expect you to memorize these sentences, everybody. So make sure that you are carefully analyzing these words, because I will be asking you to memorize these sentences so that you could perform well on your test. So the percent of variation in the response variable, so that's the y variable, that is accounted for by the least square regression line. So we will oftentimes abbreviate this the LSRL, the least square regression line. And so then S is our typical error. We're not going to be perfect when we predict. We're going to have error one way or the other, but we're going to expect that error, the typical error when using the least square regression line. Again, we would abbreviate this LSRL. Line to predict the response variable. So again, the y variable is about the value of S. So we'll be doing that a couple different times in the video lesson for today. So here's one example. This Minitab scatter plot shows the association between the size of a diamond in carats and its retail price in Singapore dollars for 48 observations. So there's 48 data entries on this scatter plot. Minitab is just a software system that many businesses use to generate data and to generate certain aspects of the data that is beneficial to the reader. So Minitab is a very common software system. So for this graph, R is 0.86 and S is 55.37. So let's understand this here. We would say that in a diamond, I remember buying a diamond for my wife. At that time I was asking her to be my fiance, whatever. There are 4 C's that you pay attention to when you buy a diamond. You would pay attention to the color of the diamond. You pay attention to the cut of the diamond, the way it's designed. You pay attention to the clarity of the diamond, whether it has any imperfections or if it's very pure. And then the last one is the one that we're talking about, is the size or the carat of the diamond. Is it a half carat? Is it a 2 carat diamond? Is it a 3 carat diamond? Whatever. So what they're saying here is that the bigger the diamond, as size increases, the value of the diamond increases. We would say that it is a linear relationship. We would say it's pretty strong and that it's positive. There's a strong positive relationship, strong positive linear relationship between the size of a diamond in carat and the price that it's worth, or the value that it's worth. So we're going to find r squared and we're going to find s. If r is 0.86, so that's telling us that it's positive and that it's pretty strong, linear. If we square it, that would give us r squared. So when we square r, we would get r squared equals 0.74. So as a percent, this is 74%. So 74% of the variation in the y variable price is accounted for by the least square regression line. I just did this right here. 74% of the variation in price is accounted for by the least square regression line. And that's what's hidden under this right here. 74% of the variation in price is accounted for by the least square regression line. So that means that the 26% that are left, those reasons could also affect the price of the diamond, the color of the diamond, the cut of the diamond, the clarity. 74% of the reason why the price goes up is because of the size of the diamond. The other factors that determine how much the price of the diamond is worth could be other factors besides just the size of the diamond. So now if we're going to predict a value, I might predict what happens if the diamond is 0.22 carats, or what happens if the diamond is 0.33 carats. I could predict the corresponding y value, and I might be pretty close, but I would expect to be off a little bit. In statistics, we're not always going to be exactly right on, but if I'm going to be off, I'm going to say my typical error is this 55.37. So the typical error when using the least square regression line to predict the price of a diamond is $55.37, roughly. So I want you to memorize r squared, and I want you to memorize this sentence s. The typical error when using the least square regression line to predict the y value, and the y value is price, is about $55.37. That's the value of s. Okay, let's practice this again. Again, this is our Minitab output. It's a very common software system that many businesses use, so it'd be a good idea for you to get used to this as well. There are a bunch of different numbers here. We're going to pay attention to 4 of them. This right here, when it says constant, the constant is another way of saying the y-intercept. The one right below it is going to be the slope of our line. And right here it tells us this is s. This is going to be what we use as our typical error. And then our r squared is our percent off that we are. Right here is going to be our r squared. So those 4 numbers you need to pay attention to when I give you an output from a Minitab software system. So let's understand this one here. Fresh Flowers, for their second semester project, 2 AP statistics students decide to investigate the effect of sugar on the life of cut flowers. Studying this some more, I guess the more sugar that water has in it, the freshness of the flower is evident longer, that kind of thing. So that's what they're trying to study here. They went to a local grocery store and randomly selected 12 carnations, and all the carnations seemed equally healthy when they were selected. When they got home, the students prepared 12 identical vases with exactly the same amount of water in each vase. They put 1 tablespoon of sugar in 3 vases, 2 tablespoons of sugar in 3 vases, 3 tablespoons of sugar in 3 vases, and in the remaining 3 vases, they did not add any sugar at all. And after the vases were prepared and placed in the same location, the students randomly assigned 1 flower each vase and observed how many hours each flower continued to look fresh. So they wanted to see, does the sugar make the flowers look more fresh longer? A scatter plot, a residual plot, and a computer output are shown below. So we're really going to pay attention to the scatter plot, and we're going to pay attention to this output right here. Okay, so taking a look here. We would generally say, just looking at the graph, that as we added more sugar to our flower water, the freshness went up linearly. We would say that as you added more sugar, the flowers stayed fresher longer. So it says here, what is the equation of the regression line? So we usually use the y equals ax plus b. And remember, we always use the hat. So y hat is going to be equal to the slope, and our slope is this number right here, 15.2. This one is our slope. So 15.2 multiplied by our x, and our x in this case is going to be sugar. We'll define that in just one moment. And then we're going to add the y-intercept. So plus this y-intercept is, I believe that says 181.2. Right here is our y-intercept, plus 181.2. And now it says define x and y. So I'm going to do that two different places. Over here, we're going to say the x variable is the sugar that's added. And then the y variable is the freshness of the flowers. And I like to have that in the relationship of our data as well. So the freshness hat, is equal to 15.2 times the amount of sugar added plus 181.2. So now that we have the linear regression line, now we can make predictions. What if I add 2.5 tablespoons of sugar? What happens if I add a half of a tablespoon of sugar? We could then predict the freshness of the flowers. What does the slope tell us? Well, the slope is 15.2. We always put the slope over 1. So this is the x variable, the change in x, and this is the change in y. So as x increases 1, we would predict that the y increases 15.2. So as sugar increases, y increases, and the y variable is freshness. So we would say something like this. For each additional tablespoon of sugar that's added, for each additional x, we would predict, you got to have that word predict in there, we would predict that the freshness of the flowers would increase 15.2 hours. So something like what I have here for number 2. For each additional tablespoon of sugar, the flowers are predicted to stay fresh for an additional 15.2 hours. As x increases 1, y increases the value of the slope, which in this case is 15.2. Okay? What is the value of r? Well, we know the value of r squared. R squared is 86%. It tells us right here. This is our r squared. So if r squared is 0.86, which is 86%, how do we find the value of r? Well, we could just get rid of the square. We square root both sides, and the square root of 0.86, if you put that in your calculator, you would get r equal to 0.93. R equals 0.93. So now that tells us, boy, 0.93, that's pretty strong. It's positive. So it's a strong, positive linear relationship between the tablespoons of sugar and the freshness of the flowers. So is this linear model appropriate? Yes, this is linear data. So now we're going to interpret r squared and s. So r squared, which is this 86 right here, 86%, 86% of the variation in the y variable, so 86% of the variation in freshness is accounted for by the least square regression line, or is a result of the amount of sugar added. There may be some other factors that affect freshness, but 86% of the effect of freshness is because of the sugar that's added. So here's what I want you to say for that sentence. 86% of the variation in freshness is accounted for by the least square regression line. Now, we could be wrong. If we're going to predict something, we would expect to be off by a little bit, not a lot, but we would expect to be off somewhere. So this S right here, this is our typical error. This is what we would expect to be off by, our typical error. So when using the least square regression line to predict the freshness, we would expect to be off by about 7.5 hours. The typical error when using the least square regression line to predict freshness is about 7.5. So if I make a prediction, maybe I predict that it's going to be fresh for, let's say, 200 hours. Well, I might be off a little bit, but I bet I'm not going to be off by more than 7.5 either way. It might be 195, it might be 205. I'm guessing it's going to be 7.5 hours or less. So that's what r squared and s tell us. Let me know if you have any questions when you get to class tomorrow.